Hi there, this is Estelle Trengove, and on this video I'm going to be doing another superposition example for the course LN 2017. Consider this circuit. In this circuit we have to find VO, which is over here, using superposition. So first we're going to consider the effect of the 1 milliamp source only. So remember that the principle of superposition is that we can consider the effect that each source has and then add them all together in the end. So we're going to look at the 1 milliamp source, which is in parallel with the 6 kilo ohm resistor. This is the 14 kilo ohm resistor. And the 5 kilo ohm resistor. And we're going to call the voltage here VO dashed, because it's not the final voltage, it's just the contribution to that voltage that the 1 milliamp source makes. And now if you take a look over here, you'll see that we've omitted the voltage source by short-circuiting it, and over here we've omitted the current source by open-circuiting it. And you can see that basically we have a current divider here, so this current is flowing, some of it in here and some of it in here, because this is a 6 kilo ohm resistor, and these two resistors are now in series, so they form together a 19 kilo ohm resistor. So writing the current divider rule for the circuit, we have IO dashed here, and IO dashed by the current divider rule is 1 milliamp times the resistor in the other branch, so times 6 kilo ohms, divided by the sum of all the resistances. So that's the 6 kilo ohm in the one branch and 19 kilo ohms in the other branch. And that turns out to be 0.24 milliamps. And now we can use Ohm's law to calculate VO dashed. So VO dashed is equal to 5 kilo ohms times 0.24 milliamps, and that's equal to 1.2 volts. And this is the first part that we need to calculate VO. Next, we're going to consider the effect of the 14 volt source only. So if we omit the other sources, our circuit looks like this. Here we open circuit the 1 milliamp source, and then we've still got the 6 kilo ohm resistor. We've got the 14 volt source, the 14 kilo ohm resistor, the 3 milliamp source has been open circuited, And here we have the 5 kilo ohm resistor, and we're going to call this VO double dashed. Now you can see that all the resistors are in series. So this 6 kilo ohm resistor is in series with the 5 kilo ohm, which is in series with the 14 kilo ohm. So IO double dashed is equal to 14 volts of the 14 volt source divided by all the resistors added together, which gives you 25 kilo ohm, and that turns out to be 0.56 milliamps. So therefore VO double dashed is equal to the 0.56 milliamps times 5 kilo ohms, and that is equal to 2.8 volts. So that's the second part of VO. And now finally we have to consider the contribution that the 3 milliamp source makes. So if we omit the other two sources, then for the 3 milliamp source only, our drawing looks like this. We've open circuited that 1 milliamp source. We've got the 6 kilo ohms. We've short circuited the 14 volt source, but we've still got the 14 kilo ohm. We've got the 3 milliamp source. And the 5 kilo ohm. And look, let's call this V star, VO star. So this will be IO star. And now you can see that the 14 kilo ohm and the 6 kilo ohm are connected in series. So in fact, we've got a current divider again, and the current is flowing like this and like this. So IO is defined in the opposite direction to what it probably is flowing like. So I star O is equal to minus 3 milliamps by the current divider rule times 20 kilo ohms, which is the 6 kilo ohm plus the 14 kilo ohm divided by 20 kilo ohms plus 5 kilo ohms, and that is minus 2.4 milliamps. So VO star is equal to minus 2.4 milliamps times 5 kilo ohms, and that's equal to minus 12 volts. So finally we can work out VO, because VO is equal to VO dashed plus VO double dashed plus VO star, and that is equal to 1.2 volts plus 2.8 volts minus 12 volts, and that is equal to minus 8 volts. So what that means is that the VO is actually in the other direction to the direction in which we defined it. On the next page, I'm going to use nodal analysis. for the same circuit so that you can see that nodal analysis gives us the same result. So using nodal analysis, we're going to first pick a reference node. So I'm just going to pick this as a reference node. We have to name the other node, so let's call this VA. And then this is also a node, we'll call it VB. And we'll call this node VC. Let's call this current I1, this current I2, and this current I3. And then you can see that this is a supernode. So let's start our analysis at the supernode. And remember, we first have to see which currents are flowing into the supernode, and they are equal to the currents flowing out. So we've got flowing in, we've got 1 milliamp, and that must be equal to I1 plus I2, which are flowing out of the supernode. Now we write the currents in terms of the node voltages. So we've got 1 milliamp is equal to VB minus VC divided by 14 kilo ohm, and that is because this current I1 has been defined as flowing from VB to VC. So this is part of VC because it's an expanded node through the 14 kilo ohm resistor. And VI2 is flowing from VA to our reference node, our 0 volt reference node. So I2 is equal to VA minus 0 divided by 6,000 ohms. And now we're going to multiply that by the smallest common denominator, which is 42,000, and that gives us 42 volts is equal to 3 VB minus 3 VC plus 7 VA. So if we arrange the terms in alphabetical order, we have 7 VA plus 3 VB minus 3 VC is equal to 42 volts. At node VC, by Kirchhoff's current law, we've got I1 flowing in, and flowing out we've got the 3 milliamps plus I3. Writing the currents in terms of node voltages, we saw previously that I1 is equal to VB minus VC divided by 14,000, and that's equal to 3 milliamps plus I3 is flowing like this. So it's flowing from node VC to our 0 volt reference node through the 5 kilo ohm resistor. So we've got VC minus 0 divided by 5,000. If we multiply that out by 14,000, we get VB minus VC is equal to 42 volts plus 2.8 VC. And if we arrange it so that we have like terms together. We can in fact find an expression for VB in terms of VC, so we get VB is equal to 42 volts plus 3.8 VC. And let's call that expression 2. We'll call that expression 1. And our last expression comes from the supernode over here. So you can see we've got the 14 volt voltage source. At the higher voltage we have VB, and at the lower voltage we have VA. So we know that VB minus VA is equal to 14 volts. So therefore VA is equal to VB minus 14 volts. So if we substitute VB for what we got in equation 2, then we get VA is equal to 42 volts plus 3.8 VC minus 14 volts, and so VA is equal to 28 volts plus 3.8 VC, and we'll call this equation 3. And now if we substitute equations 2 and 3 into equation 1, then we get 7 times 28 volts plus 3.8 VC plus 3 times 42 volts plus 3.8 VC minus 3 VC equals 42 volts, which gives us 196 volts plus 26.6 VC plus 126 volts plus 11.4 VC minus 3 VC equals 42 volts. And that works out to 35 VC equal to minus 280 volts. And therefore VC is equal to minus 8 volts, just like we got with the superposition. And that's the end of this recording.